Okay. Okay, well, welcome to the CBE 6 review. I'm Mia. I'm a Calc 1 recitation leader. This is Carly.
I'm Carly. I'm also a Calc 1 recitation leader.
Yeah. I don't know if either of you have been to a CBE review yet, but this will be recorded and the audio will be recorded. You guys aren't being recorded. So you can find this on YouTube after as well. But I think we are ready to get started. So CBE 6 will cover lessons 16 through 18. Like it says, it will cover area under a curve, definite integral, and fundamental theorem of calculus. So it's just a lot of definite integrals and kind of the application, a little bit of them. So first we're going to start with approximating area under a curve, which is done with Riemann sums. There are a couple different kinds of Riemann sums that I know all sections of Calc 1 have talked about. There's like the left and right endpoint sums. So there are the two formulas for them. So the main difference is just where you start your indexing from and where it ends. So for the right endpoint sum, you'll start at 1 and at n. For the left endpoint sum, you'll start at 0 and at n minus 1. So that's the main difference. And then you can get the exact area from estimating using infinite regions, so that's kind of where the integral comes in. So the Riemann sum is like the approximation, and then a Riemann sum, we can also get the exact area as we take the limit as n goes to infinity. This connects to our definite integrals, so we can write a definite integral as a Riemann sum. And here are the formulas for that. So n are the number of intervals we have. We'll find delta x by doing b minus a over n. And then x sub I will be a plus I delta x. So you can use these formulas to write an integral as a Riemann sum. So taking this definite integral, we're just going to find each of these things, delta x, x sub I, and just plug it into the formula. So to find our delta x, oh, why is it not writing? Oh no.
Is that pencil connected?
Might not be. Give us a second, try to connect this. Okay, now it's connected. Okay, perfect. Okay, so in order to do this, we're just gonna find delta x and x sub I. So to find delta x, I'll make that a little, okay, we'll just take b minus a over n, so that gives us 2 over n. And then to find x sub I, we will have a, which is 3, plus delta x times I. So then we can plug that into the formula. I like to kind of do this intermediate step where I just find f of x sub I, just helps me think through it. So that will be 3 times 3 plus 2i over n squared. And now we have all of the different pieces that we need to put together our Riemann sum. So we'll write it out doing the right endpoint. So we'll start at 1 and we'll go to n. And then I'm going to multiply, since we'll have f of x sub I times delta x, we'll have our 2n times our 3. So I'll write that as 6 over n. And then we'll put in our f of x sub I. Does that make sense to you guys? Do you have any questions about this one? Okay, perfect.
Okay, now we're going to talk about definite integrals and area.
So if f is a positive function, then the definite integral is equal to the area below the curve and above the x-axis. But if it's a negative function, then the definite integral is equal to the negative of the area above the curve and below the x-axis. So if it's sometimes positive and sometimes negative, then it's equal to the area above the x-axis minus the area below the x-axis, which is bounded by the curve. So it's area under the curve, but if it's underneath the x-axis, then it's negative, essentially. These are some properties of integrals we talked about. So if there's of definite integrals, so if it's the a and b bounds are the same, it's 0. We can flip our bounds and just it's equated with a negative sign, and then a constant can be pulled out of the integral. We can separate if it's just added or subtracted, you can separate out the integrals, and then we can split up the endpoints is that last one. So these are just some properties we talked about that are helpful. So our second problem is the integral from 0 to 4 of 5x squared minus 3x plus 8 dx is equal to the area above the x-axis and below the curve y equals 5x squared minus 3x plus 8 on the interval 0 to 4. Okay, so essentially what this is saying is we're going to take this integral and we want to know if it's equal to the area above the x-axis and below the curve of that function on the interval. So based on what we just talked about, what do you think? So, okay, let me like demonstrate. So essentially what this is saying is this function is both above the x-axis and below the x-axis. So do you remember what happens to the area if our function goes below the x-axis?
It's negative.
Yes. So if our function goes both above and below the x-axis, we're going to have our positive values. We're going to subtract our negative below the curve values from that to get our integral. But so in that case, is our integral going to be equal to the area? Does that make sense? Like if I have a parabola, that looks something like, it's so messy. Okay. Looks something like this, right? That's not what that looks like. But the area under the curve is going to be, my integral is going to be negative, right? And it's going to take into account. So my area under the curve is always going to be positive, but my integral is going to take these positive sections, add them together, and then subtract the negative sections. So would my integral be equal to the area above and below the curve?
Yeah. No.
So my integral, I'm putting together all these values, but I'm going to be adding these values and subtracting these values. But when I'm taking the area of it, I'm just going to be adding all those values together.
Okay.
Does that make sense? So I'm like, there's another example. Our next problem is going to illustrate this better, but let's say I have like a square. So the area, let's say this is 1, and this is -1 here. So the area of this, and I'll call this 1 over here. So the area of this square is 2 by 1, so it would just be an area of 2 units. But as an integral, the value of this is 0, because there's equal area above and below the x-axis. Does that make sense? Okay, so that's why this one is false. It should like appear on the bottom of the slide or something. Oh, there we go. Okay. You just have to click these the little side arrow or whatever, but yeah. Okay.
Awesome. And then just like Carly said, this problem is going to kind of help us think through more of the idea of area below and above the x-axis. So it gives us the graph of an equation. We don't know what the equation is, but we have the graph. And then we're going to use this graph to evaluate this integral. So we know that an integral can also be thought of as like the area under the curve or above the curve, basically between the function and the x-axis. So we can split this graph up kind of into different shapes that we're familiar with, that we know how to find the area, and add up all of the areas together. So we can start with looking, since we know it goes from -5 to 3, so our -5 is here, and then 3 is here. So it's the area, I guess the integral of the entire graph. So the way that I like to think about it is just look for all the familiar shapes that I know. So between the function and the x-axis, we have this square. And then we can find the dimensions of the square. So it goes from -5 here to -3. So the width is 2. And it goes down to -2 down here. So the area of this part will be 2 times -2, which is -4. And then right next to it, I'm gonna use a different color. There's this triangle. And so the base of the triangle would be 1. The height would also be -2. So we'll find the area of that one, which is 1/2 the base times the height. That gives us -1. And then the next shape that I will section off is kind of this big triangle. And that goes from -2 to +2. So the base of that will be 4. And then it comes up to 4, so the height is also 4. So find the area of that one, which is 8. And then we'll look at this last portion of the graph, which has that triangle, which is the same as the other triangle. 1/2, 1 times -2, which equals -1. So now that we have all the areas of the individual parts of our graph, we can just add them all together. So we'll get 8 minus 1 minus 1 minus 4, which gives us 2. I wrote over where it says solution, but so the integral from -5 to 3 of f of x is 2. Do you guys have any questions about this one? Okay, perfect.
Okay. Excuse me. Okay, now we're going to get into the fundamental theorem of calculus. So with the first part, integration can be thought of as the inverse of differentiation. So we let f be a continuous function on the interval, the closed interval ab, and let x be a point in that interval. And the theorem says that if f of x is equal to the integral from a to x of f of t dt, then f prime of x is capital big F prime of x is equal to little f of x. And if big F of x is equal to the integral from a to g of x, little f of t dt, then big F prime of x is equal to little f of g of x times the derivative of g of x. Okay, that's a whole mouthful, but it's just what we've gone over. So in this case, I have a big F of x, and I'm looking for f prime of x. So what is big F prime of x? Okay, that's a very open-ended question. I mean, it's little f of x, right? I can change the color. You know what? This is a great color because I don't know how to change it. So maybe settings. Is it settings? Oh,
Yeah.
Okay, gotcha. Okay, so these two are equivalent. So in the slide we just looked at, we have the definition that big F of x, we have an integral of a to g of x of f of t, little f of t dt, then f prime, oh wait, I take this with some complications. Okay, then we get f of g of x times g prime of x. So these are the definitions we had on the slide before. So using the fundamental theorem of calculus, in this equation, our g of x is equal to that x squared plus x. And then our f of t is equal to that e to the t cubed. So let's write our f of x. 15 to x squared plus x e to the t cubed dt. So just plugging in, we're just plugging into that e to the t cubed, our g of x. That makes sense. So it's just e to the x squared plus x cubed. And then we have to times that by the derivative of g, which is just 2x plus 1. So not that bad. You just plug in that g of x on the top into your function, and then times it by the derivative of g. Okay. Everybody feel good about that question? Okay, sweet.
All right. So continuing with this idea of like fundamental theorem of calculus, this part of it is usually called the evaluation theorem, and it's pretty much the way that we evaluate definite integrals. And it's specifically for when we have a continuous function on a closed interval, and then when we take the antiderivative or take the integral, then we'll plug in the two endpoints. So we'll plug in the top or the higher endpoint and subtract the lower endpoint. So we are going to do that with this integral. So I'll just write it out. So from -1 to 3, we'll evaluate the integral of 2x squared plus 4x dx. And for this integral, we can pretty much just use the idea of like the reverse power rule. So we know that with the power rule, we'll bring the power down and subtract 1. So the integral version of that is we'll add 1 to the power and divide by the power, like the new power, I guess. So this will give us 2/3 x cubed plus 4/2, which we can simplify to 2, x squared, evaluated from -1 to 3. So then we'll take our upper endpoint, we'll plug that in, so we have 2/3 times 3 cubed, and then I'm going to simplify this 4/2 to 2, plus 2 times 3 squared, and then we're going to subtract 2/3 times -1 cubed plus 2 times -1 squared. So to simplify this, you can just use a calculator, but I'm going to divide out a 3, so this will end up being 3 squared. So we'll have 2 times 3 squared plus 2 times 3 squared. And then -1 cubed is just -1, so we'll have -2/3 plus 2. And then 2 times 3 squared is 18, so we'll have 18 plus 18, which is 36. And then 2/3 plus 2, we can rewrite 2 as 6/3, so that will give us 4/3. And then to create a common denominator, I'll just multiply 36 by 3, which will give us 108 of 108/3 minus 4/3, which gives us 104/3, which is our answer. So we did call it something fancy. It's part of the fundamental theorem of calculus, but with definite integrals, we take the integral, plug in the endpoints, and subtract the lower bound from the upper bound.
Okay, so we're just gonna solve another definite integral. Yay! Okay, so this one, I think a little bit of the legwork for this integral comes in before you even start doing the problem. So in looking at this problem, all of our all of our numbers inside the integrand are factors, right? And so we can do a little bit of simplification actually before we start solving the problem. Does anyone see what we could do?
You move the x out. And
Yeah.
then you take out the square root.
Yes, exactly. So I can rewrite this as x squared times x to the negative 1/2. And then I can combine those exponents. Gives me x to the 3/2. Okay, and then from there, we're just going to follow a similar procedure as we did in the last one and use the reverse power rule. So we add 1 to the exponent and then divide by that as well. And we can also pull out our constant. So that gives us x to the 5/2 divided by 5/2. Evaluate it from 0 to 4. And then dividing by a fraction is same thing as multiplying by its reciprocal, which gives us 5 times 2/5 times x to the 5/2 evaluated from 0 to 4. And then I can just cancel out those 5's because they're factors. And then come down here to evaluate. So I have 2 times 4 to the 5/2 minus 2 times 0 to the 5/2. So that's just going to be 0. And then I'm going to rewrite this as a square root. So I can take the square root of this to the 5th power to evaluate it, which just gives me 2 times 2 to the 5th, which is 2 to the 6th, which just gives me 64. So not too bad. Everybody follow that one, same process of the definite integrals, but you don't just want to like kind of blindly go through it. You know, if there's something you can do to simplify before you do it, then you should take that. So
Awesome. Okay, we have another definite integral. So that's all the CBE is about. Okay, so we're just going to take the integral of cosine of 2x plus 3 sine of x. So to start, sometimes it can be hard to keep track of like which one is the negative, like the integral of cosine, is that negative sign or is it positive sign? The way that I like to think about it is I draw it out this way. So we have sine, cosine, negative cosine. And then when we're taking the derivatives, we'll like move around it this way. And so when we're taking the integrals, we move around it the opposite way. That's just one way that I think about it. You guys can think about it and remember it however you would like to. I found that helpful. I shared it with some of the students in my recitation.
That's the same way I was taught to think about it and think
perfect.
about it. So yeah.
Yeah, it's just like a nice little visual to think about. It also follows our ideas of the graphs that we draw where like the left is negative and the bottom is negative. So I think it's pretty handy. So go back to actually taking the integral now. So I have cosine of 2x plus 3 sine of x dx. Okay, so now we know that the integral of cosine is sine. And since we have a 2x in here, one way to think about it is if you were to take the derivative of sine 2x, you would use the chain rule and multiply by 2. And so since we're taking the integral, we're going to divide by 2 instead. Because then if we take the derivative of this 1/2 sine 2x, we get back to our cosine of 2x. And then the integral of 3 sine x will be negative 3 cosine x. We're going to evaluate it from 0 to pi halves. So we'll have 1/2 sine of 2 pi over 2, which will just be pi, minus 3 cosine of pi over 2. And then we'll subtract 1/2 sine of 0, minus 3 cosine of 0. So this will just be pi. Those twos will divide out. So then we'll have sine of pi, which is 0. So this will be a 0. Then cosine of pi halves is also 0. So we'll have a 0. Sine of 0 is also 0. We have a lot of zeros here. And then cosine of 0 is not 0. That one is 1. So then we'll have negative 3. And since we're subtracting a negative 3, that will end up being positive 3, which is our answer. That was pretty straightforward, sines and cosines.
Okay, I think the next one we're moving on to something different. Okay, we're going to move into some applications of integrals. So the first one we're going to talk about is average values. So if f is a continuous function on the closed interval ab, then the average value of f of x on the interval is defined as 1 over b minus a times the integral from a to b of f of x dx. So we're going to apply that in this next problem. So we're going to determine the average value of the following function over the interval 0 is less than or equal to x is less than or equal to 2, and our function is f of x is equal to 3x squared plus 4 plus e to the x. So we're just going to plug it into that function that we just had. So our average value is going to be equal to 1 over b minus a, so 1 over 2 minus 0, times the integral from 0 to 2 of our function, which is 3x squared plus 4 plus e to the x dx. So we're just going to evaluate this definite integral and then multiply it by a half. So it gives us 1/2, and then our integral, remember, using the added property, we can just kind of evaluate them all separately and add them together. So that would give me 3 divided by 3 using the reverse power rule. And then I have 4x, right, because it's x to the first power and then divided by 1. And then the integral of e to the x is just e to the x. And these are all evaluated at 0 and 2. Okay, did everybody follow to there? Okay, great. So now I'm just going to plug in those values. So 1/2, keep my big brackets. And then I have one too many parentheses. So it gives me 2 cubed plus 4 times 2 plus e to the 2 minus 0 cubed plus 4 times 0 plus e to the 0 power. Okay, and now we're going to evaluate. We'll continue to evaluate, I suppose. So it gives me 2 cubed is 8 plus 8 plus e squared. So this is 0, this is 0. So that gives me minus plus e to the 0. E to the 0 is just 1. So it's subtracting 1. So as my final answer, I have 8 plus 8 is 16 minus 1 is 15 plus e squared. So that's just going to give me 15 plus e squared all over 2. Everybody follow? Just took the 1 over b minus a and then just evaluated the integral like normal over that time. So I also wrote over the solution and so.
Thank you. Okay, so now we are going to determine the area that lies beneath this curve and over the x-axis on this interval. This is another way to state a definite integral problem. This kind of goes full circle to like the first couple of problems we were talking about how integrals help us find the area between a curve and the x-axis. So this is pretty much asking us to find the integral of x squared minus 1 from -2 to 3. So we can rewrite that as the definite integral from -2 to 3 of x squared minus 1 dx. And then just like we've been doing for multiple problems, this will kind of be like the reverse power rule. So we'll have We'll add 1 on to 2 to give us 3, so we'll divide by 3. So we'll have 1/3 x squared, and then minus x, evaluated from -2 to 3. So then to evaluate this, we will have 1/3 3 squared minus 3 minus 1/3 -2 squared minus a -2, so we'll add 2. And then I'll simplify this so we can divide out a 3 right here. Oh wait, that should be cubed. So then we'll have just 3 squared, which gives us 9 minus 3. And then -2 squared is 4, so we'll have 4/3 plus 2. This side will be 6, and then the 2 to add it to the 4/3, that's the same as 6/3, so that we can add those fractions together. So this will be, I feel like I might have done something wrong. I don't know. Okay, so 6 minus 10/3, so 4/3 plus 6/3. And then I'll just convert the 6 into a third as well, or into thirds. So that will be 18/3 minus 10/3 equals 8/3.
-2 to the third power.
Oh, 2 to the third. That's where it is. Okay, I thought my numbers were wrong because I did this earlier.
Yeah,
I keep writing a squared instead of a third. Okay, that's a third.
Is in your -4?
Yeah.
I think that's something.
Okay. Yeah, I did this earlier, so I got confused. I guess I just like squared more than cubed. That's okay. We'll just go back and fix it.
Just like even numbers, that's what it is.
I do like even numbers. 2 actually is my favorite number.
Oh, really?
So
Okay.
that could be why. Okay, that's okay though. We can just go back and evaluate it now using the right numbers. So -2 to the 3 is -8. So then we'll have -8/3 plus, and then I'll convert the 2 again, which is 6/3. So I'll have 6 minus -2/3. And then that will be 18/3 plus 2/3, which gives us 20/3, which is our answer. Okay, yeah. So just another way to phrase definite integrals. That's all CBE 6 is. Lots of definite integrals, which are great. I think that is the last problem. So if you guys still have questions or run into any troubles as you review for the CBE or take it, you can come to the Aggie Math Learning Center. One of the tutors or any of the recitation leaders come look at your attempts. You can also go to this website. You can also just look up like USU Aggie Math Learning Center on Google. And our website has a lot of information. So if you don't know, like, if you can't make it to one of the recitation leaders' office hours, you can see their others. There are lots of videos and explanations. And then this CBE will be posted on our YouTube channel as well. So thank you for coming. Hopefully that made sense. And if you have more questions, you can talk to us or come to the Aggie Math Learning Center.